I just want to look at a handful of HSC questions that have appeared over the years. Here's the first one. Comes from 2007, Extension 1. Mr. and Mrs. Roberts and their 4 children are going to the theatre. They're randomly allocated 6 seats in a row. Probability that the 4 children are allocated seats next to each other. So it's a probability question. Now there's what I propose the answer is, 3 factorial, 4 factorial over 6 factorial. Now the logic behind there, well, bottom of the fraction would be total possibilities, no restriction, so the whole sample space. And so really that's just arranging 6 people in a row. So 6 factorial is on the bottom. So what about the top? 3 factorial, 4 factorial. So the 3 factorial, well, that's the number of ways of arranging 3 objects, because really the 4 factorial, we know the 4 children have to be together. How many ways can they be arranged? 4 factorial ways. They're now a group plus the 2 adults. So there's 3 objects we're arranging, 3 factorial on the top. So all of that turns out to be 1 in 5. It's much more fun to look at Extension 2 questions. So let's have a look at this one. A bag contains 12 red marbles, 12 yellow marbles. 6 marbles are going to be selected without replacement. Now, without replacement's important, because as soon as you have replacement, it's no longer permutations and combinations. It's basic counting theory. Because all the permutations and combinations assume it's without replacement. So those formulas are without replacement. Calculate the probability that exactly 3 of the marbles are red. So exactly 3 are red. Okay, the order that we choose them does not matter. We're just selecting 3 marbles. So it's a combination. Total number of possibilities then would go on the bottom. There are 24 marbles all up. We're going to select 6 of them. So 24C6. On the top of the fraction, I've got 12C3 times 12C3 because I want 3 red ones. So from the 12, I'm going to choose 3. And I want 3 yellow ones. So from the 12 yellow, I want to choose 3. So 12C3 divided by 24C6, they set to 2 decimal places. So 0.36. Okay, so that was the first part of the question. Hence or otherwise. Now, a wonderful statement. Hence means, of course, using what we just proved. Or otherwise means, well, if you really want to, sure, use a different method. But they're trying to give you a hint here. Like, hence, you can use this first part. Calculate the probability that more than 3 of the marbles are red, again, to 2 decimal places. So if more than 3 are red, well, I could have 4 red, 5 red, or 6 red. I'm not going to use the complementary idea because it's really not going to save me any time. Because it'll be 1 minus no red, 1 red, 2 red, 3 red. So really, this is probably quicker. 4 red, 5 red, 6 red. So the denominator would be 24C6. That's not going to change. 4 red. So from the 12 red, I'm going to choose 4. Which means from the 12 yellow, I'm going to choose 2. Or, so we add, 12C5. So I'll choose 5 of the red and then 1 of the yellow. Or 6 of the red, none of the yellow. And all of that tidies up to be 0.32. That seems to be an otherwise method. I didn't really use part I, other than it's the same idea, I suppose. There is a way of doing it, it's quite neat. Here's how you would use part I. If I actually do use the complementary idea, but a little bit differently. If I say greater than 3 red, would be 1 minus, and I'm breaking up into 2 things. Probability of 3 of them are red, or the probability that less than 3 are red. Now, why did I do that? Because the probability of less than 3 red is the same as saying the probability of more than 3 are yellow. Because if you've got less than 3 red, you must have more than 3 yellow. But it's equally likely. Remember, there was 12 red and 12 yellow. So the probability of greater than 3 yellows would be the same as the probability of greater than 3 red. And so now what I'm looking at is an equation. I can move the probability of greater than 3 red to the left-hand side. I get 2 times the probability of greater than 3 red is 1 minus the probability of 3 red, which is what we worked out in the first part. So I can substitute that in and we get 0.32. So that would be the way of using part I. This one was a beauty, 2006. So we have a chess match between a home team and away team. We've got 4 boards that are being played on, 1, 2, 3 and 4. Each board, the probability of the home team winning is 0.2, probability of a draw is 0.6, and home team losing is 0.2. So in other words, equally likely either team wins there, because if home team loses, obviously the away team must have won. They're both 0.2. The results are recorded by listing the outcomes of the games. So for example, if home team wins on board, that should be board 1, shouldn't it? Home team wins on board 1, draws on board 2, loses on board 3, draws on board 4. We'd write it down as win, draw, loss, draw. That's how we'd record the outcome. So how many different recordings are possible? On each board, there's 3 possible outcomes. A win, a draw, or a loss. So 3 times 3 times 3 times 3, there are 81 possible outcomes that we could record. That's probably the gift mark of the question. Calculate the probability of the result which is recorded as win, draw, loss, draw. Now be careful, because it's tempting to just say, oh, that'd be 1 in 81. That's just one of those outcomes. But the outcomes are not equally likely, remember. Remember, draw is 0.6, whereas win and loss are both 0.2. So I actually need to work it out individually. Probability of a win, we said, was 0.2. Draw was 0.6. Loss was 0.2. Draw was 0.6, giving us 0.144. So I guess the common mistake that would have been made there was people just to go, oh, well, it's 1 in 81. But it's not. It's 0.144. All right, now we add to the game. Teams will score 1 point for a win, half a point for a draw, and no points for a loss. So we want to know, what is the probability that the home team ends up scoring more points than the away team? So the home team more than the away team. I'm going to break this up into situations. The first thing I'm going to work out is the probability of them scoring the same number of points. So I'm going to think about all the different ways they could score the same points. If there's a draw on every single board, they're going to get the same number of points. So that would be 0.6 times 0.6 times 0.6 times 0.6. 2 wins or 2 losses. And 2 losses. So if they get 2 wins and 2 losses, the 2 teams would get the same number of points. A win and a win would be 0.2 squared times loss and a loss, another 0.2 squared. But how many arrangements now can get that? So you could have win, win, loss, loss. You could have loss, win, loss, win. So in other words, how many ways could we arrange 2 L's and 2 W's? So 4 factorial on 2 factorial, 2 factorial. So it ends up being 0.0096. What else could we have? We could have 1 win, 1 loss, 2 draws. So the win would be 0.2, the loss would be 0.2, the 2 draws 0.6 squared, but again, there's different ways we could do that. So how many ways could we arrange win, loss, draw, draw? Well, that would be 4 factorial on 2 factorial. Is that every situation? Is there anything else we can have? No, that's it. Okay. So add them all up. There's a 0.312 chance that we end up with the same number of points. Therefore, logically, unequal points must be 0.688, because either you're going to have the same or you're not going to have the same. But remember, the win and the loss was equally likely. So therefore, half of that 0.688 must be where I score more points, the home team scores more points than the away team, and half of those must be when the away team scores more than the home team. So, probability of the home team would be a half of those unequal points. And we get 0.344 as the probability. Pack of 9 cards. We're seeing we were so successful yesterday with our card problem. 1, 2, 3, all the way up to 9. 3 cards are drawn at random, and then we place them on a table from left to right. So in other words, we're forming a 3-digit number, really. What's the probability that that number exceeds 400? Sometimes it's still basic probability. Greater than 400 must be 6 over 9, because what would make this number bigger than 400? And that's if the first card was a 4, 5, 6, 7, 8 or a 9. So 6 out of 9, 2/3 chance. Okay? Not everything is super, super difficult. the basics are still there. What's the probability that the digits are drawn in descending order? Now, they don't have to be consecutive, just descending. Just descending. Well, we know there's 3 factorial ways of arranging the 3 digits. So we're going to pull out 3 cards, remember, and go 1, 2, 3, there's our number. But those numbers that I pulled out could be arranged 3 factorial ways. In how many of those would the numbers be descending? 1. Therefore, the probability is 1 in 6. There's some examples of some actual HSC ones. We'll add the odd questions from 14F to our list.